Hi guys, today I'll talk to you about outliers. I'm gonna explain a little bit about outliers. I did explain a little bit about outliers in class, but today I'm just gonna explain what to do for the flipped class. I will show you an example or two and you will have to run the same piece of code for other variables on the dataset. First of all, would like you to kindly head to Moodle, and under the flip Friday, June 25th, you have the data set. This data set is basically a house sales data set. So it is, they call it a King County data set from the United States, where they have the prices, the different prices of the houses sold at a certain date. So here's the date and time, and over here there's the price. We have an ID that we don't really care about, it's just a unique identifier. Then we have bedrooms, bathrooms, number of bathrooms. I don't understand how the bathroom is 2.25, but well, this is the data that we have in hand, and we're not going to consider this as an error in entry. We're just going to keep it as is. And then we have the living room space in square foot, the parking lot, or maybe the lot around the house, and the floors, number of floors, the waterfront. Let me show you something here, just to introduce the data set to you. I'm going to add a filter here so that you can see the different possible entries. So here's the floors ranges from 1 to 1.5 to 3.5. Then we have the waterfront. It's a dummy variable, either 0 or 1. And the view is a kind of score from 0 to 4. Then we have the condition, also a score from 1 to 5, so it's kind of categorical. The grade is also a score up to 13. Then we're again going back to the square foot for the rooftop, square foot for the basement. Then we have the year built and year renovated, zip code, and then we have longitude and latitude. So these three, for now, we're not going to do anything with them. And then we have the square foot of the living room. This is, do we have square foot living? We don't, right? Basement, yeah, living. And the square foot lot 15. So I don't understand, why do we have square foot above? We have square foot lot, and I don't know really the difference between square foot lot here and square foot lot 15. As you can see here, almost the same readings, right? Almost. All right. In any case, this is the data set. We have this number of records at the moment, which is about 21,614 records. And let's begin. No, don't say. I head to my Jupyter notebook, and of course I started with importing different libraries and then reading the Excel sheet. So after doing that, you need to run the, it's going to take you a little time depending also on the strength of your computer. And over here it gives you the first few rows and the last few rows of the data set. So here we have 21,613 rows by 21 columns or variables. However, there are some variables like the ID that I'm not going to use, or the date I'm not going to use in the future, but let's, like in the analysis, in the prediction analysis, but let's for now just keep it as is and not drop any of the variables. As I usually suggest to you that you need to identify numeric columns or variables versus non-numeric. However, you need to understand that even though the ID is presented in a numeric format, that doesn't mean it means it is discrete. It means that it's continuous. Yeah, it's a numeric. It could be discrete, meaning it could be ordinal or categorical data, ordinal or nominal data. So as for now, we just wanted to make sure that we don't have any variable populated by a string, because as we studied in the previous class, whenever you have a string, you need to transform that or convert it into dummy variables or whatever kind of numerical variable that you could use for analysis, right? All right. And here the non-numerical variable is only one, it's date, so that's fine. Let's go ahead and look at the description. Here, describe, I didn't put describe all, so I just need to take a look at here some of the values. In class we can talk a little bit more about some of the values. For example, here we have like minimum, we have maximum, and we have the mean. So look at the minimum, for example, for price. The minimum is 7.5 something plus 4 here. Here plus 6, it's in millions. And then you go to the mean and it's in between. All right, not that bad. But probably the mean is about 5.4 and it's not in the millions. It's plus 0.5. So 5 more digits. But over here, the maximum is in the millions. So now I can easily tell that there are a huge number of outliers. Now let's talk a little bit about our goal. Our goal of this data set, the objective of this data set is to predict the prices of houses. So this is the dependent variable. This is the target variable, the price. Would like to predict the price of the houses by regressing it against different variables like bedrooms, bathrooms, the space of the size of the living room, the lot, the number of floors, whether or not it has a waterfront, and so on. So for now, I would like the first thing you need to do is to detect missing variables. So I'm not going to do this right now. This is your homework. I'm writing here notes because I'm going to go revisit Moodle and list down the things that you need to do, the tasks that you need to do. So first of all, you need to go over the data and check for missing values. So I would like you to do that to start with, yeah? After doing that, I'm going to show you how to detect outliers. Checking for missing values shouldn't take you more than 5 to 10 minutes, really, right? It shouldn't. So this is a 5 to 10 minutes a task to do before you detect outliers. So first detect missing values, and now I would like you to detect outliers. Let me just put this here just in case. And here we put all right. And here. All right, you need to do that. And comment on it. So detect missing values first and comment on it if you need to comment, really. Okay, detecting outliers. First of all, I would like us to look at it visually. I would like to detect outliers visually. One of the things that we do is detecting outliers by either the box plot or the histogram, especially that we're using continuous data and our dependent variable is a continuous variable. So first of all, let's take a look at this code. What is this code? First of all, let me remind you of SNS. SNS is actually this library, the Seaborn library. So from this library, we'll be able to plot the box plot. The data here is the DF that we've just read, and the orientation is horizontal for all the variables. And here we go. You just put palette set. You can just get rid of this. What is this? Let's take a look. So over here, you have different color. Here. Oh, it's okay. Okay, it's either one or two. So okay. So over here you have like a red color. Over here you have like a green color. So this is what the palette is for the color. Now over here you can see that ID is we actually don't need ID, but if you have a very huge data scale, this data scale is really different and varies, then you will have a very difficult time visualizing the rest of the variables. So the alternative way or course of action is to create a box plot per each variable, or to group the variables in terms of their scale. So for example, let's go back here and take a look at our variables. First of all, we have the price, and the price, as you may probably noticed in the description here, the maximum, the minimum, quite a big number. So I'm going to keep the price separate in terms of scale. When it comes to bedrooms, it's just the maximum and the minimum and max is like 33 to minimum, sorry, is 0 to 33. Then we have here bedrooms or bathrooms 0 to 8. Then we have also number of floors ranging from a minimum of 1 to a maximum of 3.5. So we can tell here that maybe floors and number of bedrooms, the bathrooms, kind of similar in scale. However, if we take a look at the square foot of the living room, the size of a living room, and the size of here the rooftop, the size of a basement, and the other square feet, kind of like variables here, starting with square feet, they also belong to the same scale, similar scale. So let's try to group these variables accordingly. I would like you to pause the video right now and bring a piece of paper and a pen and try to list down the variables and group them together. I would like you to drop ID. Don't drop it as of yet from the data set. It just, for now, don't worry about visualizing and detecting outliers for the following variables. ID, I really do not wish for you to explore ID, of course. It's just a unique identifier. Let's also not take into consideration the year built and the year renovated and the zip code and the latitude and the longitude. The lat is a latitude and the long is the longitude. So usually latitude, longitude, and the zip code are like location-based kind of variables for now. I do not wish for us to worry about these variables. And also the year built and year renovated, not for now, okay? So would like you to just let go of these variables as of now and try to group them in terms of scale. Okay guys, so the previous, the second then task was for us to group the different variables into similar scales. And this probably took you about 10 minutes. So for now, I would like to show you how I've done my grouping. So I put it into different data frames, like I had data frame 1, data frame 2, the group 2, and data frame 3, group 3. In data frame 1, I don't know why, I started by copying all these. Do you remember when I told you it's a good idea to identify numerical variables? So in the output of this, I just copied the output of this and I used it to define a data frame. So here is a definition of a data frame here. So over here I put all the variables and I started then taking out some variables. So ID, date, latitude, longitude, year built, year renovated, and zip code, I left it as is. So this is the data frame that I'm not going to use. These are variables we're not going to use for now or explore. So the second data frame, as you can see here, is bedrooms, bathrooms, and floors. They're similar in scale, aren't they? Then we have the third data frame is all the square foot kind of variables. So I don't need the extra spacing here. So all these is starting with the square foot. They have the similar scaling. Then I have the waterfront and the view, and then I have the condition and the grade. Now let's see how I used the box plot, the same code for the box plot. Let's see what is this different. Yeah, so it's the intensity is different in the color. Okay, so I used it to do visualization. So I said VDF2, visualizing DF2. And then I use the data frame _2, and I produced this box plot. As you can see here, look at this crazy outlier in the bedrooms. So we have this very distant outlier or reading in the bedrooms. We have also a bunch of outliers. Did I explain in class? Probably did not. I wonder if I had enough time to explain in class. Let me show you something, guys, about the outliers that I haven't had the time to explain in class probably. Okay, I'm just going to remind you of what it means to have a quartile. So this is a series of data: 3, 7, 9, 12, 14, 15, 17, 18, and 40. The minimum value here, the 5-number summary or the 5-number statistics, is the minimum 3, the maximum here 40, and then we have the median. The median is 14. Once we have the median, the minimum, and the maximum, then we will be able to identify the or slice the data into quarters. So we're going to have the median here in between the minimum and the maximum. Then we're going to pretend as if this second half doesn't exist, and the minimum is a 3 and the maximum is 14, and then we border or identify the median. And here's the median is 9. This means that from 3 to 9 we have the first quarter of data points, the count in terms of a count. Then we have from 9 to 14 we have the second quarter of data. Now this second half that we outlooked earlier, let's also split it into halves. So 14 being the minimum, 40 being the maximum, the median here would be 17. And this, as you can see on the figure, will in fact identify the third quarter from the 14 to 17, and then the fourth quarter from the median here, 17 to 40. So now we understand that any data set as small as this or as big as the data set that we have could be sliced into different quarters for equal counts of the data points: first quarter, second quarter, third quarter, and fourth quarter. So now how do we use this to identify outliers? Outliers are distant readings in the data set. So here's the smallest value. This is the median. This is the median. This is another median, and this is the largest value. So basically, the lower quartile here is Q1 or first quartile. If you remember here, that was the first quartile. So the first quartile is also called the lower quartile. And here, this quartile is called the upper quartile. Here is quartile 1, 2, and 3. So here quartile, the upper quartile is 3, which is this one, is the fourth number in the okay. So we're just talking about the lower quartile as a number. So the lower quartile here, not as a range, the lower quartile, this is quarter 1. Yeah, sorry guys. So this quarter 1, this is quarter 2, this whole range is quarter 3, this whole range is quarter 4. Now a quartile is one numeric value. The lower quartile is quartile 1, and Q1 or quartile 1 is the median of the minimum and the median. Now a quartile, the upper quartile, is actually this value, which is the median between the median of the whole data, the global median, and the maximum. So again, we have the ranges between the minimum to this median, quarter 1, identifies quarter 1, and the median of the median and the lower value, the range between this median and the global median is the second quarter, then this is third quarter, this is fourth quarter. This value, the median between the minimum and the global median, is called the lower quartile or Q1. This median value produced from the median, the global median of the data set, and the maximum value is called quartile 3 or the upper quartile. So the upper quartile here, in the lower quartile here, 25% of the data lies below the lower quartile, while 25% of the data lies above or larger than the upper quartile. Now let's define the inner quartile range, the IQR. The inner quartile range, as you can see here, is this range between the lower quartile, this first median, it's actually the second median, this is the first median, second median, third median. So this is the range between this lower quartile and the upper quartile. All right, how do we use this to compute outliers? To determine if the number is an outlier, we multiply the inner quartile by 1.5. The inner quartile range here is 17 minus 9, which is equal to 8. We multiply then the 8 by 1.5, which produces 12. So how do we use this number 12? An outlier will be any number that is 12 less than a Q1, the lower quartile, or 12 more than the upper quartile. So 17 plus 12 is basically 29. So any value that lies above the 17 plus 12, which is 29, is considered an outlier. 18 is lower than 29, so it's not an outlier. 40, on the other hand, is greater than 29, so 40 is signaled as an outlier. Let's take a look at 9 and 12. 9 plus 12 is basically 21. 7 is less than 21. 3, wait a minute, it's not 9 plus 12. it should be less. Yeah, it should be less. So let me show you this here. So you need to subtract 12. So 9 here minus 12. So all the way until minus 3. Yeah. So any value less than minus 3 will be considered an outlier. 7 is definitely greater than minus 3, and 3 is also greater than minus 3. Therefore, these values are not outliers. If we had a value here like minus 4, then minus 4 is less than minus 3, and thus it is an outlier. So this is how we use or detect outliers with the box plot. So first of all, we identified the median of the data. First of all, actually the minimum and the maximum, and then the median in between. Then we kind of split the data and identified the lower quartile. The lower quartile is the median between the minimum and the global median. Then we identified the upper quartile, and the upper quartile is the median between the global median and the maximum value in the data. Then, having the Q1 and the Q3 identified, we can compute the inner quartile range, which is basically 17 Q3 minus Q1, which is 17 minus 9. And then we got the number 8. Multiplying 8 by 1.5 yields a 12. Then we use this 12 in the following manner. For Q3, which is the upper quartile, we add the 12. So 17 plus 12 is 20. 7 and 2 is 9. And then 1 and 1 is 2. I'm sorry, I put here 39. It's 29. So it will be 29. Any value greater than 29 any value greater than 29 will be identified as an outlier. With the lower quartile, we subtract the 8 times 1.5, which is 12. So 9 minus 12 is minus 3. Any value beyond this 3 or greater than, less than minus 3, because minus 4 is less than minus 3. Any value beyond minus 3 or less than minus 3 will also be considered as an outlier. So this is how we do it. Also would like to show you how identifying an outlier helps computing a healthy mean. So the mean was 15. The mean in fact, when there was no outlier, or when there was an outlier, the mean was 15 and the median is 14. However, when we got rid of the outlier, we found the mean to be 11.875 and the median to be 13. Alright, this is how we use the box plot to identify outliers. So this is why it is very important for us to use the box plot to identify outliers. So as you can see here, this is a whisker. This is the IQR, the inner quartile range. So this is the inner quartile range, and the whiskers delineate the 1.5 range. Yeah, so any value beyond, outside this whisker or this whisker will be considered an outlier. Now that you understand this, back again to our code, we are going to plot the other values here, but it's still very difficult to see the outliers. I can still see that there are some outliers. It's still very difficult to put them all in one let's see what happens if we do that. Same situation, vertical or horizontal is all the same situation. Okay, so I decided to plot the Whisker plot, to use it to plot the Whisker plot for each variable separately. So here we have the size of the rooftop. Here we have the square foot of the basement, the living, and here is the lot 15. So many outliers, right? And here there's so many zeros as well. All right, if you take a look at the data frame 4, which is basically the waterfront and the view, there isn't much to see because waterfront is either 0 or 1, and the view is categorical values. So this is what happens when you attempt to use the Whisker box plot. It's considered a very good visualization to detect outliers in numerical values, and you apply it on categorical values. Doesn't make sense. So here, maybe I should just write here for some students here, using the box plot on categorical values does not make much sense, or actually does not make any sense, to say the truth. Alright, so over here let's take the data frame 5, which is the condition and the grade. Seems like even though they are kind of a bit categorical, but they're not really. It's more numerical here. So we were able to see, yeah, condition maybe is not that helpful, but for grade is quite helpful. I don't think I would like to correct the data for grade or condition due to the design and the nature of the data. So I'm not going to correct this at all. These are not in numerical values. And this is why I tell you, understanding the context is very important. Grade, as I've showed you earlier, a grade has the values ranging from, let me show you here, a grade has the values ranging from minimum 1, maximum 13. So definitely this is not much of, over how many records? 21,000 almost records. So this is, I would call it no touch. Do not touch these two variables for corrections, really. Alright, let's see what happens when we take a look at price. Price is the dependent variable. So now I'm going to say here, so let's focus on the dependent variable, or the target variable, which is the response variable, meaning that it responds to any variations in the independent variables. So the price would respond positively when the number of rooms are greater, meaning the price would go up when there are more rooms or more bathrooms or bigger lots and so on. So it responds to the independent variable. In any case, for regression, we call it a dependent variable. With dependent variable here, we can see that we have many outliers. This is the first thing I would like you to detect. Also, there's a different way of plotting these box plots. There's another piece of code that I usually use here, as you can see. This piece of code helps us, I think it's over here. This piece of code over here helps plot all the box plots for all the variables. Do you see that? So view, as you can see, is ranging from 1, 2, 3, 4. So it doesn't make sense here. Grade also, be careful with the grade. It's ranging from a certain number, minimum 1 I think, to 13. By design and nature, this is not really numerical, so we don't have to worry about grade or condition. This we need to worry a little bit about. Zip code also by design, we don't need to worry about it. As you can see, this is date, so we don't need to worry about it either. This one also. Here we need to take a look. The lot here is all right, as you can see, almost all right. Okay, so let's take a look. Most of the box plots displayed above show possible outliers. While some box plots do not do this accurately, like for example there's 33 bedrooms, others report outliers that make rather logical sense, like houses renovated in the year 2000 or a house having a condition rating of 1. Yeah, so as I told you, condition, for example, and view or the renovated date is not really to be considered for outlier detection. So this is also a nice piece of code. I probably should put it a little bit up over here. Let me just add it over here, guys. How about price? I don't have price here. It's over here. Oh, wait a minute, where's price? Here. You can see a lot of outliers in price. Yeah. Alright, so that we established that there's a lot of outliers in price, which is a dependent variable. Let's dig deeper. Digging deeper, I'd like to take a look at the distribution, at the histogram. In principle, I won't care much about the independent variable distribution. I will care only about the dependent variable, mostly at the first glance. I will focus mostly on the dependent variable, which is price. So I'm going to draw here a histogram. So this piece of code here, just one line of code, helps you create histograms with, here bins is auto. You can change the bins if you want. You can write a function for the bins depending on the method that you would like to use. For now, I would like to see price. I can't see much of price here. So let's take a look at the data in general. Here we have modularity. So you have like a bit of a pattern here and then another pattern. Here you can see that it is kind of left skewed because the tail is to the left. Here modularity and the skewness to the right. Here a bit of a skewness to the right, skewness to the right, skewness to the right for price. Price is very important to show a normal distribution. If we are using regression, one of the assumptions is to have the price being normally distributed. So over here this is also right skewed and this is left skewed, and there's modularity. Modularity means that there are like two bells. Over here also we have as if we have two different data sets. So let's focus on price for now. Away from outliers, first thing first is the price here. Before correcting outliers, there's also the distribution. One assumption for using regression, as you may guys know because you all took regression in statistics, is for price to be normally distributed. What does normally distributed means? Normal distribution. So normally distributed means it looks something like this. Can you see that? So here the skewness should be 0. It is not tilted to the right, not tilted to the left. If it tilts to the if the tail is to the right, then it will be positively skewed. If the tail is to the left, it will be negatively skewed. So how about kurtosis? Kurtosis is basically when this which one is the normal distribution? Let's assume the red is the normal distribution here. So with kurtosis, you will have either the peak going up or the peak going down or either shifted also. So this is the normal distribution. With the normal distribution you have the mean here, and 68.2% of the data points will lie within 1 standard deviation away from the mean. And then about 95.4% of the data will lie in within 2 standard deviation away from the mean. And then 99.7% of the data will lie within 3 standard deviations of the mean. Then whatever goes outside the z-score of 3 will be considered an outlier. Regarding skewness, the skewness should be 0 if it's really normally distributed in a very ideal manner. And I'm going to talk a little bit about the skewness in a bit. So the output shown above also helps us understand the shape, the skewness, the modality of each distribution. Several features such as price, for example, the size of a living room, are skewed and of course unimodal. But these distributions also shine a light on which variables could be considered categorical and which are definitely continuous, right? You can easily see that, yeah? Here and here, for example. All right, so let's take a closer look at the histogram of price. But this, I don't like it much actually, this one. But in any case, regardless, that's actually a note that I added to the box plot. So if you noticed in the box plots that we've done just earlier, most of these box plots of course display outliers, possible outliers, and yeah, we've already read that, so it's okay, just need to move it. All right, so now if the skewness is 0, the data is perfectly symmetrical, so it's normally distributed, hopefully. Although it is quite unlikely for real-world data to be not skewed. As a general rule of thumb, if skewness is less than -1 or greater than 1, the distribution is highly skewed. If skewness is between -1 and -5, or we say if it's between -0.5 to 0.5, then probably it's fairly skewed. I already explained a little bit more about the skewness here. Oh, excuse me. So let me over here show you how to get the skewness of price, for example, which is the dependent variable. We check the skewness, as you can see here. The skewness here is 4.0, which is considered high. I'm gonna also I think I can copy that, in fact, the whole thing, and move it up, but it's okay. Just take it here. I have a very precise or brief explanation. Now, how do we deal with the skewness? So the first thing I advise to do is to deal with the skewness, because if you deal with the skewness, you could get rid of outliers. So the first way is to get the skewness here, and then depending on the situation and the skewness type, you can correct for it. We correct for it through transformation, or transformation we call it. First type of transformation is the square root. The square root is basically to give a square root of to take the square root of the price. So you have one column of price, and then the other column of the other variable that you create is the square root of price, and this is what you're going to use. The square root method is typically used when your data is moderately skewed. So when is the data is moderately skewed? I have here excuse me, these very interesting lines that I would like to put up also for you. So with when the data, when the skewness is from 0.5, it's the to 0.5, from 0.5 to minus 0.5, it's very symmetrical. When it's between 0.5 to 1, or between minus 0.5 to minus 1, is moderately skewed. When it's moderately skewed, then you can use the square root transformation. And when it's skewed to the right also, right? So when it's moderately skewed, using the square root here is a transformation that has a moderate effect, and it's generally used to reduce the right skewed data. This is the square root x, in fact, for Excel. Okay, log transformation. When do we use the logarithmic transformation? To take the logarithm of the price. The logarithmic is a very strong transformation that has a major effect on the distribution shape. And this technique is usually used also for right skewness, and used when we have a high skew data. So for example, any value less than -1 or any value greater than 1. So if you have a skewness of 1.5 or 2 or 3 or 4, this is considered highly skewed. So log transformation is the right transformation to use. Then there's other transformations. As you can see, this transformation is for categorical variables, but we also have other different kinds of transformations, but the most used ones are the log transformations and the square root. Sometimes in some relationships, like for example the advertisement spend and the sales, there is a relationship here between sales and the advertisement spend. As the time passes, the more you spend, you won't be able to get the same effect. So the effect of advertisements fade over time. Yeah. So no matter how much money you spend over a certain period of time, this advertising effect will fade. So this is what we call it, the diminishing effect. With the diminishing effect, for example, we take the power of the variable. So we have to raise it to a certain power to transform it. So these are very kind of like special cases in marketing. So now that we've done this, actually before we delve into that, and let me just put here something important. Before performing actually we could also do that. Another very important piece of or an assumption that you need to test or examine is the linearity. So you need to kind of have, for numerical variables like the house price, by the way, the house price is supposed to be on the y, So there's a mistake here. Why does the price needs to be on the y-axis? Because as this is the house prices on the y-axis, and here we have to have the house price here, the y label, and this is here the basement size. Alright guys, please pay attention to that. So because as the basement size increases, the assumption is that there is a linear relationship. So it seems like as the price or the size of the basement increases, there will be slight increase in the prices. So the same applies here. So please make sure guys that you have a price in the rooftop. So over here, as the size of the rooftop increases, moving this direction to the right of the x-axis, something happens to the response variable on the y-axis. So always the response variable, or the target or the dependent variable guys on the y-axis. Actually, we shouldn't use response. There's a specific conditions and context where you use the response, but for now we just use dependent variable here. So please make sure that you, as a third task, please examine the possible linear relationships between the dependent variable, which is price, and other numerical variables. Of course, with categorical variables, it's hopeless case. You don't have to put in, there's no such linear relationship visually detected. Now, visually, outliers here are detected visually by looking at the extremes, at the far extreme of the x-axis. So this far extreme, this two, and the far extreme of the y-axis. So these guys on the y extreme. So all these, like the y extreme on top or the x extreme here horizontally to the right, these are all considered outliers. Why? Because the density of the data, as you can see, the data is more dense around here. All right, very good, very good, very good. So this way we can examine all linear relationships. So please do this to all numerical data and examine the linearity. Having this done, I'm gonna now work on the linear transformation. Linear transformation here, I'm gonna take, I've done that. I'm going to take this. Before the linear transformation, in fact, I would like to show you a very interesting piece of code and organize it for you very nicely over here, which is basically, you guys know how to add here a new line. It's escape and B. So hold down the escape button and the B, or you can just insert cells above or below. So over here I have the description of the code above. We're using the skew and the kurtosis methods so that we can, and the transpose, so we can read it easily like that vertically. So you can in fact take a look at different skewness. Over here there's major skewness here and major skewness here, definitely over here as well. So I'm going to talk about kurtosis later, but this is also a nice piece of code that you could use for generating skewness for all the variables that you have. Now let's correct price. Correcting for price is as follows. Actually, before correcting for price, I'd like to examine the distribution a little bit closer. So this is examining the distribution of price very closely, so you can see easily how it is distributed and how it has a right tail. And now I would like to see the distribution after correction and to correct it. So let me correct it as follows. I'm going to skip one line on purpose. So over here, basically this code is saying store in df price, which is the original column, store in df price the following. From NumPy, take the log for log transformation, this method, and then apply it on this variable, price from the data frame. Then from the Seaborn library, distribution plot the distribution of the df price. But now df price is becoming the log distribution. And then plot the figure. So basically you can see the difference now. This used to be very highly, the kurtosis is also easily you can see that it's so shooting up and skinny, and it has a tail, so it's skewed. And over here it is kind of considerably has become nicely and normally distributed. So we kind of fixed the problems probably of outliers over here, didn't we? So if you want, I'd like to show you before we get any further, would like to show you here the values. But now I cannot show it to you because price has already been transformed. So this is if you want to see how log price has this, if you want to explore that NumPy log, how did it change the data. So you can see how the data is now ranging from 2 all the way to 2, so it's around all 2. Yeah, so that's a very strong transformation and very successful one. So you can just, you know, explore the data here after transformation. Okay, do you want to take a look at the box plot now after this transformation? Why not? Let's do that. So I'm gonna just take the box plot for price. Now I'm gonna plot it again after the transformation and see how it will look like. I hope it works though. Oh, it still have outliers. So even though that you corrected the transformation, you corrected for the normality a little bit here, you still have outliers. So we still need to correct the outliers. So all what we've done right now is getting the distribution to become normal. And then we have reduced the number of outliers. And then now we can deal with these outliers. Look at the plot. Keep a memory of this plot, visual memory of this plot. Compare it with this one. Where is price? Over here. Do you see? So now we are getting rid of not only there are so many houses were considered outside the upper quartile as outliers, upper quartile times 1.5 of course, while here you can see that we're also considering very cheap houses to be an outliers, which is more realistic, isn't it? Yeah, isn't it more realistic that we consider the very cheap houses and the very expensive houses to be outliers, and we focus on the houses condensed around the mean. So now this is just a preparation. All this that we've done is just a preparation for us to detect outliers And in the process of detecting outliers, we were able to correct for the distribution, for the normal distribution. So instead of the skewness here, the sharp skewness and kurtosis, we were able to kind of clean it up a little and make it more normally distributed. Yeah. So I think, guys, I had recorded so far about 1 hour, and I've given you tasks for about 30 minutes. This is it for today. Please generate all the graphs to examine the linearity here between the dependent variable price and all the numerical variables, as well as a check for missing values at the very beginning of our investigation. Alright guys, thank you so much for today. I'll see you again on Tuesday, and on Tuesday we are going to work together on correcting outliers, and yeah, and hopefully we can finalize regression by the end of the semester. Thank you so much. See you on Tuesday.